We defined speed the other day as just simply how quickly something's moving, how fast something's moving. Velocity was real similar, but it had a more technical sounding definition. It was the rate of change of position. But in the end, they both boiled down to almost the same thing. Speed was distance over time, how much distance you traveled in a certain period of time. Velocity, because it's the rate of change of position, is displacement over time. Now, tell me when those two numbers are going to be the same. When are speed, average speed that is, and average velocity going to be the same number? It's going to happen a lot, right? When? When you're going in a straight line and not changing direction. And of course, they're going to be different numbers when you are changing direction. So if I happen to go to the north, then to the north again, my average velocity will be the same number as my average speed, but it'll have a direction associated with it because it's a vector. If I happen to go north and then south, my speed will be a certain number, but my velocity will be a different number. Can you tell me which number is going to be bigger? Now, sometimes they're going to be the same, right? But if they're not the same, clearly one's going to be bigger. Which is the one that's going to be bigger always, unless they're the same? Speed or velocity? Bruce? Speed, yeah. Because think about that. Speed is a scalar. So the numbers to get distance, we always are going to add together. Now, displacement, we're sometimes going to add them together, we're always going to add them together as well, but sometimes we're going to add a negative value to it. So sometimes displacement is the same number as distance, but sometimes it's a smaller number than distance. Therefore, velocity will sometimes be smaller than speed. What units do we typically use for distance and displacement? What's the typical units there, Kelly? Yeah, we're going to use meters for distance and displacement, and we're going to use seconds, yeah, seconds for time, although we don't have to, right? When we did our homework last night, question number 6, Bruce used kilometers per minute. Is that okay? Is it okay to use kilometers per year? Yeah, it'd be a really strange unit to use kilometers per year, but it's correct, right? We don't always have to use meters in second. It's just that that's the standard units. Sometimes we have to. Okay, in a couple of days, you're going to find that we have to use meters per second for a lot of questions. But right now, we don't. If in doubt, though, if you're not sure what units to use, if you're not sure if you can use units other than meters per second, then use meters per second because it always is going to work for us. All right, a couple more quick questions, and then we'll check over the homework that we had last night here. When we're calculating velocity, or speed for that matter, sometimes we have to find displacement or distance first. What are the two ways that we can find displacement? What are the two ways that we can find displacement, depending upon what we're given? Okay, everybody know one way that we can find displacement? Yeah? Okay, if we're given positions or displacements, yeah? If we're given positions, what are we going to do with them? Subtract them, right. So if we're given positions, we're going to say displacement is df minus di. If we're given displacements, then we're going to say that displacement, the total displacement, is going to be the displacement number 1 plus the displacement number 2. Or there could be 2 or 3 other displacements that we have to add together as well. Now, the question that you had is question number 6. Required you to do that. It required you to find the total displacement and then divide it by the total time. We look at this question number 6, and a lot of us right off the top think, okay, wait a second, I got 90 kilometers per hour, then I go 100 kilometers per hour. What's my average speed? 95, right? Add them up and divide by 2, right? Let me give you an example to illustrate why that doesn't work, okay? Let's say I'm driving to Edmonton. Let's say it's 300 kilometers. It's actually a little bit more, but let's say it's 300 for ease of math sake. Okay, it's 300 kilometers. And let's say that I'm driving at exactly 100 kilometers per hour the whole way. How long is it going to take me? How long is it going to take me? Yep, 3 hours, right? But let's say I stop in Red Deer, gasoline alley there in Red Deer, because I want a drink and I want a snack and bathroom break, whatever. Okay, and I stop for 15 minutes. When I stop for 15 minutes, how fast am I moving during that time that I'm stopped? This is not a trick question. Okay, how fast am I moving during that 15 minutes that I'm stopped? Zero, right? So I'm going 100 kilometers per hour for 3 hours, and I'm going 0 kilometers per hour for 15 minutes. What's my average speed? Is it 50? No, of course not. Why isn't it 50? Why can't I just add up 100 and 0 and divide by 2? Why can't I just average in the way that you were taught to average in grade 6 or whatever it was? What's wrong with that? What's wrong with saying 0 plus 100 divided by 2? Yeah, Jonah? Good. That's the important part right there, right? Two different lengths of time. If I traveled for 100 for 3 hours and then I was stopped for 3 hours, that would actually work, right? 100 plus 50, sorry, 100 plus 0 divided by 2 is 50. But it only works, as Jonah said, if the time is the same. The time isn't the same here, so I can't say 90 plus 100 divided by 2. It would be rare that you would get a question where the time is the same. So if it is, then you can say 90 plus 100 divided by 2, and that works. But usually that's not going to work. Usually we have to do something else. Usually we're going to have to go back to the tried and true equation that we learned a few days ago, distance over time. But we don't have the distance, so what are we going to do? Nick, what are we going to do if we don't have the distance? You don't have to give me specifics here, but just generally, we want to, okay, get the distance. And we're going to get the distance by multiplying speed times the time. Good. We got two intervals here, right? We got 90 kilometers per hour. We got 100. We'll call this D1. And we're going to say 90 kilometers per hour. Let's do it as displacement because we're going to need that for velocity, right? Positive is east. 90 kilometers per hour times 10 minutes. Probably want to go hours there, right? 0.167 hours, I think. When we do that, it should work out to be, I'm not sure. I don't have that number written down, actually. What is that? Is it 15? 14.4? I think it should be exactly 15, shouldn't it? I think it's exactly 15. Because if I think 90, this is 1/6 of an hour. 90 divided by 6 would be 15. I think it's exactly 15. So during that stretch, we go 15 kilometers to the east. Now during the second stretch, we're going to say that's V2 times T2. That's going to be 100 kilometers per hour, actually negative 100 because it's to the west, times, this is an easier one, 0.5 hours. Multiply those two together and clearly we get 50 kilometers here, actually negative 50 kilometers. I think I made a mistake though, question when I gave you the answer there, I think. I think I did. What's the total distance? Yeah, 65 kilometers. What's total time? 10 minutes, 30 minutes, 40 minutes, 0.67. What does that work out to be? Oh, sorry, wait a second. Yeah, no, I didn't make a mistake. I was looking at the wrong number here. That should work out to be 97.5 kilometers per hour. Is that right? Or 27.1 meters per second. How many people got that? Good. Excellent. That's the trickiest question we've done so far this year. Okay, it is. Okay. V equals D over T, we've done that a bunch of times, right? Adding the distances up to get D, we've done that a bunch of times, right? But knowing that we had to get the distances and then add them up, okay, that's the tricky part with that. Hey, let's, even though we didn't have to convert this to meters per second, let's just do that as practice, okay? 97.5 kilometers per hour. We're going to convert that to meters per second by doing what? 97.5 kilometers per hour is 97.5 times 1,000, 97,500 meters per hour. Do one at a time, right? Convert kilometers to meters, 97,500 meters per hour, and then let's convert hours to seconds. So on the bottom, we have 1 hour, or we have 3,600 seconds, which is the same thing as 1 hour. And when you do that math, it should work out to be 27.1 meters per second. Good. Now, question B isn't that much harder. If you got question A, my guess is that you got question B correct as well. But here we're finding the average velocity. It's just displacement over time. And since we've already done the lead-up work in question A, there's not much work to do in question B. The displacement is going to be, what, 65 again? 65, right? Alex, what's it going to be? Good. How come negative 35? Yeah. This is a time when displacement is different than distance, right? Because we've changed direction. 15 to the east, negative 50. 50 to the west gives me negative 35 kilometers. And my time is still 0.6667 hours. That's going to work out to be 52.5 kilometers per hour. How many people got that one? Okay, you weren't asked to do this, but I'm going to ask you right now, everybody at your desks right now, to convert 52.5 kilometers per hour to meters per second. If you forget how to do it, follow along in green there, right? There's your guide. 52.5 to meters per second. Holly says the answer is 14.6 meters per second. She's correct. We're going to say 52.5, 52,500 meters per hour in its first step, and then we're going to say 52,500 meters per 3,600 seconds, which works out to be 14.6 meters per second. Good. How many people got that? Good. All right, everyone. Nice little review sheet here now based on the video clip that you just watched based on the movie Triple X. Question. We're going to go over all of these questions here now. See if you got them right here. Question number 1 says, according to the Guinness Book of World Records, the fastest recorded speed for a snowboarder is less than 50 miles per hour. That's still pretty fast, right? It says less than 50 miles per hour. It's kind of almost inferring here that it's not very fast. It's less than 50 miles per hour. That's pretty fast, right? You can imagine if you're snowboarding at 50 miles per hour, it's almost 100 kilometers per hour. Stu Zander, he's the character that was in the video clip, is the world record holder, and he can snowboard this fast. He can snowboard at 50 miles per hour. What is his speed in meters per second? As I was walking around, seeing what you guys were doing, looked like you guys are doing a really good job with this unit conversion. That's good. Hey, I threw this out at you because I wanted to see what you could do with a new unit conversion, one that you've never done before. Miles per hour. Okay, we give you the conversion factor here. I think the best way to handle this is a ratio, set up as a ratio. We know that 1 mile per hour is 1.6 kilometers per hour. Let's get it in kilometers. Let's get his speed in kilometers per hour. 50 miles per hour is going to be X kilometers per hour. Now, some of you, as I was walking around, I noticed just knew to multiply those two numbers together. And if you can do that in your head, figure out, oh, it's multiply as opposed to divide, that's great. Okay, some of you aren't as good at that. That's okay too. If you're not as good at knowing whether to multiply or divide, just set up a ratio like we have here. 1 is to 1.6 as 50 is to X. Let's solve for X. Solving for X, although that requires some rearranging, right? Solving for X, okay, we want X on the top. We're going to multiply both sides by X. It becomes 1 times X over 1.6 equals 50 over X times X, right? Multiply both sides by X. And we get X over 1.6 equals 50. And then we take the 1.6 up by multiplying, right? Multiply both sides by 1.6. X over 1.6 times 1.6 equals 50 times 1.6. And I think it works out to be 80 kilometers per hour there. Okay, that's not my answer, but now I've got kilometers per hour, and I know already how to convert that to meters per second. So let's do that. Let's say 80,000 meters per hour equals 80,000 meters per 3,600 seconds, which I think is 22.2, I think it was, isn't it? 22.222 meters per second. Good? 2 says a typical power avalanche moves at a speed of between 60 and 90 meters per second. Is it possible for Xander to outrun the avalanche as in the movie clip? And why or why not? No calculations here beyond what you've already done. Why is it or is it not possible for him to outrun this avalanche? He did it in the movie. I mean, they don't put things in movies that aren't true, right? That can't really happen. So he must be able to outrun it. Say no? How come? Yeah, the avalanche is traveling way faster than him. Even if he's going as fast as a snowboarder can possibly go, the avalanche is still, at worst or best, whatever, is beating him by, what, 38 meters per second? And if the avalanche is traveling at 90 meters per second, then it's beating him at about 68 meters per second. Okay, so no, it's absolutely not possible for him to outrun that avalanche. 3, assume Xander is snowboarding at the record speed of 50 miles per hour or 22.222 meters per second. The avalanche is moving at the lower limit of 60 meters per second, so it's a slow avalanche. And he gets a 10-meter head start of the avalanche. How much time would elapse between the time that the avalanche starts and the time that it catches up with Xander? Assuming that it's all going at a constant speed, we're going to say V is equal to delta D over delta T and solve for T. You guys remember how to do that? How do you do that? Yep. T times V, yeah. We're going to multiply both sides by T, right, to get T on the top. So we're going to say V times T is equal to D over T times T, but T's cancel, right? So I end up with V is equal to V times T. But I'm only looking for time, right? That's okay, because we needed to go through that step to get time. Now we've got to do one more step, though. Now that we've got time on the top, which is what we needed to do first, we got to get rid of the V. So how are we going to get rid of the V? What is it? Divide it, right. So we're going to say V times T over T equals D over T. What am I doing here? Should be dividing by V, right? Yeah, back to the start if I do that. V times T over V equals D over V. Now I'm going to cancel out those V's, and I'm up with T is equal to D over V. The distance that this avalanche has to make up on me, or on Xander, is 10 meters. Here's the tough part, though. What speed do I use? Do I use 60 or 50 or 22.2 or some kind of combination of those? Who thinks they have this one? This is the toughest question on the page by quite a bit. The avalanche is not traveling 10 meters, neither is Xander. But the avalanche is traveling 10 meters relative to Xander. Does that make sense? So Xander has to travel, Xander travels 80 meters, the avalanche has to travel 90. If Xander travels 12, then the avalanche travels 22, because it has to make up 10 meters on him, right? So the distance that we're saying the avalanche travels relative to Xander is 10 meters. Well, if we're going to use the distance relative to him, then we need to use the speed relative to him. How are we going to find that? The avalanche is traveling at 60. He's traveling at 22. The avalanche's speed relative to him is... Kelly? No? Okay, let me ask another question. If the avalanche traveled a distance of 75 meters and Xander traveled a distance of 65 meters, What's the distance the avalanche has to travel relative to him? 10 meters, right? How'd you get that? So we subtracted, right? So if we want to find the distance that the avalanche travels relative to him, then we have to subtract the two distances. If we want to find the speed that the avalanche travels relative to him, then we have to do what? We have to subtract them. So Rudy Ann, we're going to say 60. No, was it you? I thought it was you that was. No? Okay. 60 minus 22.22, right? Which ends up being, what is that? 37.777, I think. Which gives me a time of 0.2647. So, if you ever find yourself 10 meters in front of an avalanche and you're the world record snowboard holder, then you've got 1/4 of a second before this avalanche catches up to you. How far would he travel before the avalanche caught up with him? So how far? He'd get down the hill a little bit, right? Because he's got 1/4 of a second to get down the hill. How far would he go? Well, D is equal to V times T. The distance that he is traveling is 22.222. And the time that he has to travel before it catches up with him is 0.2647 seconds, which gives me a distance of 5.9 meters. So picture this. 5.9 meters is about from this wall over to about here. So he would get from there to here in 1/4 of a second in the time that it took the avalanche to overtake him. So the good news is he wouldn't have much time to think about his impending doom. So my favorite part of the clip there was Xander at the end of the clip, he grabs onto that antenna, and you can see when he grabs onto that antenna is kind of swaying back and forth. And then the avalanche overtakes him and buries him, and then he digs himself out and has that great line at the end. Ooh, fresh powder. He's able to hold on to the antenna as the avalanche passes over him. He's able to dig himself out. There's a very clear indication earlier in the clip that the avalanche has far too much kinetic energy for this to ever be possible. What was that indication? Anybody catch that? Anybody catch that, Kelly? Yeah, that shed, it destroyed it like it was nothing, right? It takes kinetic energy to destroy that shed. Well, clearly, if it had enough kinetic energy to destroy that shed, it's going to have enough energy to knock over that antenna and to do some pretty serious damage to him as well. Good.